So good morning, everybody. Welcome to Heidelberg. Welcome to the Troopers IPv6 Security Summit. Quite a few of you have already been here, so they are familiar with the setting. For the other ones, I will give some hints what to expect in the next days and some hints as for the logistics. Very quickly, my name is Enno. I'm somewhat involved in the both the foundation of the company running this event, and which is actually in the interim, it's 3 companies with different, say, areas or disciplines. I will comment on this in more detail on Wednesday. For the moment, for today, it's just maybe relevant that I've been involved with IPv6 since 1999. Actually, I gave a 1999, I gave a presentation or a talk in an academic setting at an Universitätsrechenzentrum at the time with an experimental IPv6 stack on Windows NT4 connected to the 6-bone. Some of you might still remember that type of network. And funnily enough, at the time, I concluded that talk with the prospect of, okay, next year, from 1999, we will see IPv6 going. And in 2000, I was invited to give the keynote at some networkers event, laying out trends in IP. And actually, I laid out 3. One I've forgotten, the other one was always voice over IP, and the third one was IPv6. And again, I was like, okay, next year we will see this thing going. As probably everybody in the room knows, it hasn't taken the momentum expected or hoped for, maybe momentum at the time. There is some momentum in the interim, which is why some years ago we decided to set up, given we are a mostly security company, decided to set up this event to discuss the particularities of IPv6, especially when it comes to security, which is the IPv6 Security Summit. Again, welcome to it. Good to see you in Heidelberg. Just a quick overview, what's going to happen in the next 2 days. There will be, at least today, there will be 2 tracks. One will be chaired by myself. The other one will be chaired by Christopher, who is right now giving the basic attacks and defenses piece over in the other room. Feel free to change rooms anytime you want. There is no, like, you're not bound to stay in this room. I don't even feel offended if anytime you just walk over to see, oh, what's going on there. My colleague maybe sent me a text message. There's some nice attack stuff or demo, whatever going on. Feel free to change any time. Obviously, there will be a lunch break. In the afternoon, it will go on with 2 tracks. You can look at the agenda yourselves. I'm not going to discuss any or mention every talk happening today. I mean, you're probably here as you have realized there's many interesting things going on. Tomorrow, we will have 3 tracks. There is one very, hands-on oriented workshop going on in the morning, run by Jeff. Jeff, are you here? He's over there. Who has been an IPv6 veteran as well. One thing to mention is we will have a shared dinner tonight at 7:30 p.m. It is in the restaurant is called Hirschgasse. It's a very nice, old, very decent place. Point is, it's quite far away from the PMA. You can walk there, and actually it's a very nice walk. It's going through the Philosophenweg, Philosopher's Path. So it's a scenic walk, but it's like roughly 4 kilometers. So it's up to you if you want to head there by foot. Otherwise, we will take a bus from here, which leaves at 6:30. Just for the logistics planning, as that space doesn't have unlimited seats, Obviously, for everybody of you, there is a seat. It's the question just is anybody of you not joining the dinner? Okay, I just have to get an idea. So some speakers who are already in town have asked if they can join. I just have to know maybe how many seats there might be vacant. Other than that, I don't have too much logistics information for you. Restrooms are on each floor. There will be breaks with some drinks and snacks and all this. I hope you all feel familiar in Heidelberg and you will all enjoy IPv6 dinner, which is why we jump in directly into the core topic of my talk, which is titled Developing an IPv6 Enterprise Security Strategy. The thing here is it's about IPv6, obviously. It's about a strategy, like come up with something, an idea how to tackle certain tasks, how to be able to identify what is important, whereas what might not be that important or doesn't have to be prioritized when it comes to, say, implementing security controls. And in the title there is this mention of enterprise, so this is focused on, say, large and complex organizations. So this might include a level of politics or level of, say, different departments being responsible for different things. I will take all these into account, and actually this talk is based on some case studies, some environments we have been involved in doing this exact thing. And it turned out, in the end of the day, it's about three main steps. That is, first, gain an understanding what are the most relevant threats, and I mean a threat in itself might not be, a threat is something bad that can happen. The more interesting question is, okay, if it happens, what is the associated risk? What is the probability, the likelihood, what is the impact if it happens? Are we vulnerable to something? To put the threat into context, then it's discussing risks, and usually discussing risks is more interesting or more important for prioritizing tasks than just discussing threats. The thing is, at this point, usually it makes sense to not just discuss IPv6, but to keep an eye on what are the differences. I will get back to this in more detail later. Then obviously, once we have an understanding of what are the bad things that can happen and are those relevant for the individual organization, it's about, what can we do or what is most suited to do. And this step is usually focused on the infrastructure layer. So what can we do from the network side? I think it makes sense to discuss this much more, to discuss this, what can be done on the network layer than what can be done on the host layer, like what can we do on the individual systems. There will be another talk tomorrow on that angle. We won't cover this in much detail in this one. And another interesting question is, okay, we already have security controls of whatever types. We have firewalls, we have, say, processors of doing things, patching, log analysis, whatever. Can we just take our security architecture as is and move it to v6? Like replace v4 addresses by v6 addresses and we are done. That is another interesting question, and it should be part of like the thing that I'm going to discuss. So these are the three main topics within this talk. And the main question obviously is, okay, once we are going to deploy v6, what are the changes security-wise, risk-wise? What can we do like to address potential risks? And what can be done like with maybe new controls, new things to be deployed, and what can be done with existing ones? And what we usually see is get an understanding of what we recommend. Again, I will lay out in a second why we think this is so important. Get an understanding of the, say, threat and risk level in an IPv4 network first. Then have a look at what are the differences once IPv6 comes into play. Again, discuss controls on two different layers. When it comes to this, let me stay here for a second. When it comes to this baseline threat analysis, we have noticed it's quite important to do this actual step, which at the first glance might not be, well, it's about v6, isn't it? So why discuss v4? For two reasons. First, there might be people in your organization taking a stance of, oh, we have heard v6, there's so many security holes, we shouldn't deploy this at all. You might find these voices and opinions. To counter that, it might be important to understand, okay, well, there is this maybe security issues of v6, but before is issues as well. So it's important to understand, does it get worse? Maybe it gets even better. I can tell you it doesn't get better. Let me state this for the moment, but still, one has to understand what has been there before. Just to be able to discuss with the people who are like, oh, the sky is falling, v6 has so many security issues, everything will be broken. On the other hand, there is usually you meet people who take the stance of, well, you know, we've seen all this in before, so what's the point about v6? We don't have to do anything. We just use the stuff we already have. As will turn out, this is not the right stance either. So to be able to interact with those two groups, and I'm pretty sure that some of you have had these discussions in your organizations. It's very helpful to actually be able to understand and somewhat document what has been there before, what's the differences, which of these are relevant, and then be able to identify the actual areas of where action is needed. In the past, this is an approach we used, say, some years ago. Some of you have been in workshops that I gave in the past, and you might recall actually this one, this slide during the security day, which we used as a kind of decision matrix once discussing security problems of v6 to get a better understanding, are these worth acting on, or are these, can we ignore those? And this decision matrix was based on, okay, first understand, is this relevant? If so, has it been there before, or is it new to v6? If it has been there before, have we done something on this? For example, when you discuss NDP, spoofing, falsifying information that is exchanged as part of the ND process, there has been an equivalent in the v4 world, which is ARP spoofing. So one could take the stance, well, it has been there before, so we don't have to act on this. Then the question comes up, well, did we do anything in the v4 world? In most organizations, actually, not much has been done. There has been, like 10 years, a feature called ARP inspection, dynamic ARP inspection, DAI. Not many of you, we have not seen this in many networks. So depending on your perspective, you could either say, well, that's not a new thing, so why bother with it at all? Then it becomes interesting, okay, is this, maybe this, say, attack vector or issue has existed before. Then the interesting question is, well, is it worth, what is the impact, actually? Is there a higher risk associated with this one than there has been with before? On the other hand, you might have those people, again, the second group, well, v6 is pretty much the same as before, we don't have to do anything. For those, well, it's interesting to understand, okay, is there a risk delta? If there is a risk delta, what actually, should we address this? Should we take a stance of, well, with v6 everything is new and we can cure all the sins of the past? All the things we haven't done, we can do them now? I strongly advise against this approach. V6 in itself is, deploying V6 is a complex task. Don't overload this task with like, well, now that V6 comes into play and we have to touch everything anyway, we can redesign our network and we can redesign our security architecture. This will most probably overload the whole task. But this has been a way of tackling it, how we tackled this, like, is it new? Is something new? Is it worse? What are the differences in the past? But this one requires a good understanding anyway. We have changed this approach a bit in the interim and in the last projects, say in the last 12 months that we did in the space. We have taken a bit different path, which is we have grouped the existing, like, what are network-based security issues in v4 networks from a, say, an abstract perspective. By the way, of course, all this will be, the slides will be available directly, pretty much directly after the talk. You don't have to take notes like noting stuff that is here. You might, of course, by the way, if you need paper or pens, there is enough of this here. Raise your hand if you need to take notes. Otherwise, again, the slides will be published anyway. In those recent projects, we have first tried to come up with a grouping. Okay, what are the security issues what have been the security issues in v4 networks? And we came up with this classification, which is pretty much first and foremost, there's all types of traffic redirection attacks. ARP spoofing is an attack where you redirect traffic either of one single host or of a whole segment once you ARP spoof the default route, and that works. Actually, it doesn't always work in v4 networks, as for example, Cisco devices. They have a kind of built-in protection. Once they note a gratuitous ARP packet showing up with their own IP address, they react immediately. Some milliseconds later, they send a packet like, no, it's me. Actually, I'm the real router. Well, it hasn't worked in the last years, but still the thing is, it's a traffic redirection attack. Falsifying DNS information to divert traffic is a traffic redirection attack. Playing with routing protocols, a traffic redirection. So there's this class of attacks. Then there is a class of attacks which we call, again, attacks against provisioning information. Like once you interfere with DHCP in a certain way, modify DHCP information, modify the default route, modify the DNS, modify whatever type of parameter. This goes against the provisioning. There are several flavors of denial of service. Denial of service can happen once you exploit given properties of a protocol. You exploit the way a protocol is supposed to work, but you use it in a way that hasn't been foreseen or reconsidered by the designers of the protocol. You might just create a lot of packets. You might, like there was this ping of death thing, insufficient implementation. Once you send a malformed packet, as it's called in the, like in Cisco space, some of you might know all these advisories having this malformed packet causes device to reload. This is denial of service, not based on load usually, but based on, say, building invalid packets. And then there is a class of attacks which we call just unauthorized access over the network, which includes all, say, attacks, which mean you can reach a system, maybe which wasn't supposed to be reached, and there might be like services listening on ports. Those services might be protected or not. Once you abuse the IP connectivity of a system to actually be able to exploit a condition on the system, that is what we call unauthorized access over the network. And we will see why we will have explicitly included this one in this classification. Now that you have maybe a a list of things that were possible in IPv4 networks. The next question is, okay, how does this change in IPv6 networks, which can be broken down to what are the actual differences of IPv6 on a, say, attribute or on a protocol level compared with IPv4, which then, having a closer look, might have some security relevance. From our perspective, there is like 4, 5, 6 main differences on a, say, technical level of where IPv6 is different from IPv4. First of all, there is a much higher complexity. I won't discuss this in very much detail. For most of the, you will note on many slides, say an additional link in this part of the slide. We have a blog where we regularly publish IPv6 security-related articles, and many things that I can just touch briefly have been discussed in more detail there. When it comes to this complexity, there is different definitions of complexity depending on which one you take. It actually turns out V6, there is more protocol interaction, there is more helper protocols, those have more like options and fields and stuff, there is more interaction. We can expect there's more players overall from the perspective of complexity that we usually use. It's fairly safe to state complexity in V6 is higher than in V4. Then there is the thing, extension headers. I'm going to cover this in more detail in a second. We have a different provisioning paradigm. In V4, parameter provisioning was done by DHCP. In V6, there's another thing. We have a mostly new, it's not really new, but the role it has in V6 is different, a protocol called MLD. There is a predecessor of MLD, IGMP, but IGMP hasn't been enabled by default on most systems in the V4 world. In V6, MLD can be observed on pretty much all systems. It's there from the beginning. It's enabled by default. It has a certain role, and this brings new, as we will see, security challenges. We have there is maybe less maturity when it comes to stack implementations. Like this thing, ping of death. In V4, that was like 97 or so. And everybody was like, okay, Windows patched this at some point, it's done. Funnily enough, in like 2012 or so, the exact same type of attack reoccurred over V6. So apparently the maturity of stacks is, as we will see, is not the same as with V4, which has to be taken into account once you discuss, say, a security strategy. And there is all these transition technologies, tunnels and stuff, which have their own security issues. I've already mentioned the complexity is much higher. This is not least because there are so many RFCs specifying behavior. These RFCs are not always, say, closely followed by the vendors. We have mainly Antonius, has done a lot of lab testing, and we published a paper a year ago on how, say, different operating system stacks behave in certain conditions, and it actually turned out that once you look at, say, certain settings of router flags and DHCP being present or not, and being present in a certain way, it turns out, say, common operating systems behave very different in the same network environments. So a certain state of configuration on the network level, and then you have a heterogeneous operating systems nodes, and they don't do the same stuff. which again adds to the complexity of, and this is can be attributed to this slide, the high number of, say, evolutions and stages and RFCs in the IPv6 world. I would like to explicitly mention the role of extension headers. An IPv6 datagram can be thought of like a chained sequence of things. Hi, Sebastian, you will like this one. The thing is on a technical level, as probably most of you know, and we have discussed this area extensively in earlier editions of the V6 Security Summit. And there will be a talk as well on this one right after the opening thing by Antonius, how the extension headers can be used to circumvent ACLs. Well, assuming that you all know what extension headers are, the thing is, from a security perspective, they are highly problematic as there might be different types, they might have different sizes, they might occur in a different order in packets. You might have the number of occurrences might vary, and actually they might contain different fields. All this means that an IPv6 datagram can be somewhat thought of like a function of different input parameters, which in the end of the day means that anything you want to do, like security enforcement based on the packet content, becomes much harder in the IPv6 world. As in IPv4, well, there have been options, but they haven't been used too much, and there is a certain maturity of handling the IP options, especially when it comes to security enforcement. In IPv6, a datagram is a bit like a fuzzy entity. You don't really know in advance how big it's going to be, how many headers it's going to have, and all this, which again, from a security perspective, which usually implies you have to understand what's going on in the network. This becomes much harder once extension headers are part of the equation. Another difference that should be kept in mind is in IPv4, a router is exactly this, is an entity which forwards packets based on certain decisions, usually based on the destination address of a packet. In IPv6, routers have an additional role, which is parameter provisioning. They not just act as entities forwarding packets, but they act as entities telling, informing, say, the nodes within in a subnet about their way of getting an address, potentially the prefix part of the address, potentially other parameters, which might even include DNS. So routers have a different role, which obviously has a security impact, especially taking in mind that the trust model of IPv6 is, say, a very benign one in the sense of on the local link, we consider everybody as trusted. Like, oh, that's all brothers. If I receive a packet on a local link, I assume it's from an entity which doesn't want to cause harm, which, from like a social and a human level, is a nice approach. The thing is just, is this a realistic assumption on the network? Maybe, maybe not. Taking into account that routers, that these are packets circulating on the network, router advertisements, which have a role, which have a huge, important role, and these packets do not have any authentication, integrity protection whatsoever. This particular combination, well, should be kept in mind when it comes to discussing security of IPv6. Last one to explicitly mention is the role of MLD. Just a quick recap, MLD, multicast listener discovery, is meant to inform routers, the MLD queryers, about multicast groups, systems on a segment interested in. You might have a position like, well, we don't use much multicast in our network, so why use it? Point is, there is a very unfortunate mention of MLD in a certain RFC, 4861, if I recall correctly, and that one essentially says, well, MLD is used for neighbor, for ND, which in turn means every operating, or pretty much all operating system stacks have MLD, they have it enabled. So MLD happens, as probably quite some of you will already have seen, like in Wireshark. Unfortunately, MLD can be abused in many ways. We gave a talk on this at last year's Troopers. If you're interested, have a look at this one. There's all types of bad things that can happen once you abuse MLD. The most important one, you can pretty much very easily flood the complete link by just putting out MLD, unauthorized MLD queries. MLD doesn't have any authentication or something. Anybody can come up and ask anybody else, who of you is interested in which multicast groups? So if I ask this question, apparently right now in this room, that's not too many people, but imagine a network with 200 hosts, and all of them reply, and they reply with sending a reply for each of their multicast groups. So you have a high amplification factor. With MLD, it's very easy to flood a complete link or to DOS the network device. We brought down Cisco ASRs with just one host sending packets. And in the end of the day, RSAs became unresponsive. This is a specific IPv6 problem. So taking all this into account, we came up with this table. The organization of this table is as follows. There is the classes of attacks we have identified for the v-forward with the specific attacks or threats. We have assigned, like, okay, usually in a, say, somewhat typical environment, in v4, we consider the associated risk as high or low or something. Of course, all these, say, values can be discussed, and there can be debates around this. Just let me state, we have been in the network, say, field quite a few years. ENW, we are pretty much exclusively a security company, and we do a lot of security assessments and testings, which is, I think, we have, well, one should be cautious about the perception of the own work. But I think we have an understanding what is relevant and what is not. And then we added a column here for, okay, how does this change in a, again, more or less typical enterprise environment? Does it get better? Does it get worse? And taking those two into account, one can come up with like a prioritization. Like, okay, something has been a problem before, say at least a medium problem. It gets worse now, so we have to take care of this. If there is something like which has been a problem before but doesn't exist any longer in IPv6 or gets better, why care of it? If it has been a low problem before, and even if it changes, it might still be a low or medium problem. So this one actually is, gives an indication what to take care of, usually in a mostly typical enterprise environment. What are the things to focus on? You can't actually address or mitigate all bad things happening. You have to focus on those most relevant, and this is exactly what this table is meant for. Now that we have an understanding of what are the things we should actually address from a security perspective once v6 comes into play, it's about, well, okay, what to do, what actually to implement. And as mentioned, I will start on the, say, what I call the infrastructure level, network and network design and configuration of network devices. And we think, and in the, again, in the projects we have done in this space in the last, say, 12 to 24 months, we have usually focused on three main areas, which is isolation on a routing layer. I will discuss in a second what this is about. Then traffic filtering, mostly in transit, not on the host level, like the destination, but on the network level, be it on firewalls, be it by means of ACLs. So for packets passing, actually, devices. And there is this thing called first hop security, which is usually implemented on the switch infrastructure. Let's have a look at those. The first one, what we call isolation on the routing layer. There's 3 potential approaches which can be discussed in this space, and all of them, the common factor is, this is about, say, routing and reachability of systems as a whole. This is not about actually filtering packets based on properties, but all the things that can be discussed in this space have in common that it's about, can I reach a system, a specific system or part of the network at all, based on, say, layer 3 configuration in the broadest sense. The first thing that comes to mind here, and which we actually see widely discussed in many environments, is what we call selective announcements. Keep in mind here that many organizations actually plan to use global addresses only for their V6 networks. There's good reasons for this. I can't discuss these reasons right now in this session, but we might be able to do so over dinner or at another point. I can, from just first-hand observation, I can say that pretty much all of our customers, at least, plan to go with global addresses for their corporate networks. This, in turn, means, as opposed to maybe RFC 1918 space in the IPv4 world, that addresses are going to be used, which, from a routing perspective, I mean, that's why they are called global addresses, which can be reached from anywhere in the internet, potentially, which in itself can cause all types of security discussions, which in turn is why people come up with the idea, wait, even if we have, say, received /29 network from RIPE in Europe, which is the most common case again, becoming the so-called LAR, and receive so-called provider aggregated address space from the European Registry Organization, RIPE NCC. Well, now we have this address space and we use it in our corporate network, but we don't have to make it visible for the outside world. We can just pick certain chunks, usually /48 networks, and just propagate those from a routing perspective. So we don't make our full space and environment visible routing-wise, but we just have certain pieces of this, our, say, DMZ networks in a broader sense, which are visible. From a first glance, this makes very much sense, and we see it quite often discussed and planned for. The thing is, there is this thing called strict filtering, which goes back to certain behavior in traditional provider, traditional carrier space. And this strict filtering goes along the lines of, well, traditionally, providers have expected that other providers, routing-wise, propagate their full address space, as the expectation was, oh, this is other providers. They have multiple exit networks anyway. They can route within their network. So they are not supposed to just propagate a part of their address space, but to propagate the full of it. Not least to save TCAM memory on the routers of the other players. Just propagate one route as opposed to a few or many smaller routes. Which again is why, say, some providers actually filter on this, on the size of networks and the type of networks. Is this provider space? If so, we expect to see so-called full aggregates as opposed to see smaller segments of it, routing-wise. This has to be kept in mind once you think about this approach. Another approach could be like, well, propagate a full network, but identify beforehand some parts of the network which must never be reachable from the outside world, like R&D departments, like loopback addresses of network devices. So once I can come up with an idea, here are things in my network which should never be reachable from the internet. I can, while propagating my full address space, I can still null route, black hole route these specific networks once packets enter my network. This is a completely different approach. In the first one, space and just propagate pieces of it. In the second one, full propagation, but identify pieces which are then pretty much immediately routed to def null once entering the network. This is actually what we see most often, given it might be, it's easier to implement, to identify things that should never be reachable. Maybe, or in quite some networks, to identify that parts of the network that should be actually reachable from the outside world, especially taking like a 3, 5, or 10 years perspective into account. Actually, for example, we have one customer which initially they had planned to go with this approach. Then it turned out that they will heavily use Office 365, which meant, well, there is a large client segments which will talk to outside entities. We can't go with this approach. Let's switch to this one. Another thing in this space is what we call the reduced hop limit in specific segments. That is, let me fix this first. A quite innovative idea, which somewhat has the same intent as this one. Once I can identify parts of my network which should not be able to talk to the outside, again, R&D, R&D departments hidden in the secret woods of my corporate network, why not go with a reduced hop limit? The hop limit can be distributed as part of the of route advertisement. Actually, it's one of the core parameters. Drill down the hop limit, which then means even if a packet can come into this network, the response packet just has a certain reach and can like never leak outside of my network. This is an interesting, innovative idea. We haven't seen this in practice so far, and we recommend being very cautious about this one. Well, you might think about this, but do so only once you have a good understanding of the things going on in your network at all. This, again, the strict filter issue has to be kept in mind once you think about the first approach. There is still providers doing this. We think that the number of providers actually doing strict filtering is decreasing. There's a growing number of routes in the actual V6 routing tables out there in the internet, which don't have the so-called covering aggregate, but which exist on their own as /48 routes. So the trend goes towards the direction it's, say, permitted, or it's potential. It can be used. Just announcing smaller routes, but still it has to be kept in mind that there might be cases where it doesn't work, which in turn is why we strongly recommend to include a question about this. Actually, there's two. In the questions you ask your uplink providers when it comes to V6. We think it makes sense to have a set of questions like about actual properties of their V6 offerings, and one question there is here like a provider is willing to accept V6 prefix advertisements from the organization's space up to /48 without a covering aggregate. This has actually this was developed in a customer environment that has a very high weight, and the expected answer is yes, we do this. Once customers ask for this, probably stick filtering will go away at some point. So that is the first thing that should be part of like your strategy. What can you do on the routing level? The second one is what can be done filtering-wise. When it comes to traffic filtering, again, it's right now it's about IPv6 specifics. It's not about like, well, inbound traffic to your web server farm. You will just allow a port 80 and 443 maybe there or something. This is not what it is about, but what are the actual changes when it comes to v6. And when it comes to v6, the following things should be kept in mind or discussed or be part of the actual strategy, described somewhere, the approach a certain organization is going to take, how to handle extension headers. What about IPv6 specific, say, network addresses, which are not supposed to be well used in the internet? Is there any specifics about ICMP-v6? We will see yes. And another thing which is usually part of this discussion is what about performance impact of filtering in transit. When it comes to the performance impact, this is actually again from a one-to-one copy of one that I used in a certain organization. As for like filtering in transit, one has to keep in mind that usually on say enterprise level or even like provider level equipment, the architecture of those devices is you have a core entity, is usually called the route processor, and this route processor uses, well, it has a CPU and it uses a certain type of memory, TCAM memory, which is expensive, and you usually want to reduce, say, the number of operations and stuff actually involving this route processor. As the stuff is done in software, it has a performance penalty. And then you have, say, a layer, depends on the actual platform, but a layer, what is, say, on the RSA, Cisco RSS, is called the ESPs. Say a hardware layer which can perform certain functions, and these functions can be performed by means of, say, ASICs. So they can be performed much faster, but there's a limited set of operations which can be done on this layer. So from a performance perspective, usually you strive for do as many tasks as possible on this, say, again, taking RSA, RSR as a sample on the ESP as opposed to the route processor, or on talking about CAT65K, whatever can be done in a line card, avoid doing it on a route processor. Now, one has to know that first, whenever logging is involved, logging pretty much always involves the route processor. So you should be, from a security perspective, like logging violations is a good thing. From a network perspective, and I'm an old school network guy, it's wait a second, every log packet means the route processor is involved, which is performance-wise a bad thing. Second, when it comes to filtering ICMP or say filtering traffic by Cisco space by ACLs, this means that you might generate as a response to a drop packet an ICMP v6 type 1 packet administratively prohibited. That packet has to be generated, and this is usually done by the route processor, which you want to avoid performance-wise. And the third one is, depending on the type of ACLs you use, how those are built, they or the keywords they involve, this might be part of the, once it's with certain keywords or without certain keywords, they have to be processed by the route processor. keep this in mind. I've discussed this in much more detail in a dedicated blog post. It's not like, wait a second, well, with V6 we filter the following stuff and you drop all violations. This is about filtering in transit, and filtering in transit usually means like includes your internet uplinks, your edge devices, or say border gateways, depending on the terminology you use. Be careful with certain types of filtering, and especially when it comes to logging. What is usually done, and what we observe in most environments, is when it comes like to internet border gateways. First, talking about ICMP. Usually type 1 to 4 is permitted. You need this stuff for proper operations, especially packet to big, due to like the MTU and PMTU discovery thing. So allow this stuff passing through transit elements. I'm a big fan, and fortunately most network people I talk to allow ping and pong as well. And obviously, say even on your internet uplinks, there is a peer with whom you interact, at least at the device, the BGP peer. So it might make sense, well, to allow neighbor discovery as well on that specific link. You can drop the rest. I mean, there's not many ICMP types left, but this is a very common approach when it comes to filtering in transit. The only thing is, once you drop the rest, there is this implicit deny any at the end anyway. Think about logging. Actually, I've just been 3 months ago in an environment where they decided explicitly against logging. They said they were like, okay, this isn't our internet uplinks, 10 gig interfaces, and then like 3 to 5 gig average throughput. Drop the crap without logging it. That's just noise. So this is about filtering ICMP. Then there is this thing with extension headers. That's say an area of fierce debates. Anyway, within the ITF and within other circles, we usually recommend, and we see people doing this, and we think it has a good benefit versus impact ratio. Drop hop by hop, drop destination option, stop routing header without questions. You don't need the stuff coming into your enterprise network. And you might even go with dropping fragmented traffic. I'm of the opinion it's worth it. And you don't break much stuff. There is some discussion about DNS and DNSSEC. I've written a lengthy blog post about this. I won't have this discussion here right now. This can be like dropping all fragments can be discussed, and you might, once you have seen Antonio's talk later on, you will see why it actually might make sense to do this. Thing is, there is this slight, small possibility you break something with this, so you have to weigh these factors, but the 10-second version is drop the stuff. In an enterprise network, I'm not talking about like provider networks where your actual duty is to transport packets regardless what they are. But when it comes to protecting your own network, you don't need this stuff, and it just causes security harm. There is this like, oh, is there any addresses which address space which should never occur as source addresses? Actually, there's plenty of them. You can deny them in, say, some filter set looking like this. There is some special addresses which should never occur as a source address of a packet. You can deny a number of like address-based, perform a number of denials. Another approach which actually Eric brought up and usually recommends, and I very much like this, is not denying some stuff, but identifying, okay, what could be the potential valid source addresses of traffic? which usually is from the 200:3 prefix. This is globally routed space, except for the, say, documentation address. And you, those of you looking at actual log files have probably noted there's many, right now, many packets showing up with source addresses from this space due to like misconfigurations and test networks, whatever. So deny this before, allow globally routed space, allow link local addresses to be able to interact with your peers, neighbor discovery of a BGP peer and all this. Maybe allow this one, the unspecified address as part of DAD. I don't even think you really need this, say on a transit network with just 2 BGP peers. You don't need DAD there, but from a like standards perspective, you can allow this and deny all other addresses. This should be for like an infrastructure device, just filtering out noise and crap. This should be a good approach. Or actually, we have customer environments which go with this approach. Just a note on back to this extension header stuff. All these samples I gave here are from Cisco space when it comes to, well, traditional firewalls. Be aware that quite many of them, Checkpoint being the most prominent sample here, drop pretty much all extension headers anyway. So if you have this discussion in your environment, it's like, well, you should know that firewall vendors do this anyway, and nobody complains. So you can do the same. On firewall 1, the behavior can be modified by touching a certain configuration file. Let me state, I have a background in Checkpoint operations for many years. You don't want to touch this file manually. So the actual approach is here. Checkpoint does not really give you an option to modify this behavior. They just drop the crap, which is, I think, a good approach here. So this was the whole area of filtering. Then staying in the realm of network level controls, there is the thing called first hop security. First hop security is, say, it has been, like, I wouldn't say a marketing term, but a summary term for a number of, say, security measures, controls, parameters, which are usually applied on the layer 2 level, which means on the switches or in a Wi-Fi, say on the access point level. So once a packet gets into the network for the first time, have a look at the packet, and if certain conditions are fulfilled, drop the packet. This is part of pretty much all like security strategy discussions we see in enterprise environments. How to handle first hop security, which measures of a set of potential measures to apply. It should be noted that the main use case for first hop security is the access layer switches. First hop security can be or could be deployed like in the data center as well, both on the physical and on the virtual infrastructure. But this heavily depends on availability of certain features. While we pretty much all common enterprise level access layer switches, be them from the Cisco, HP, Brocade, whoever, those can have these features in the interim. The picture is completely different when it comes to data center, and especially to virtualized switches. Cisco Nexus 1000V doesn't have it, whereas Microsoft Hyper-V does have a very good, actually, first hop security implementation. On physical Nexus, it depends. It's not really yet there. So while these features, again, access layer, availability is good. When it comes to data center, it's not so good. First hop security, especially, I mean, Cisco kind of invented this stuff. It's, as I mentioned, most other vendors have this stuff too. The especially in Cisco space, usually one differentiates between different generations. There has been a first generation, which, by the way, has been discussed at the V6 at Troopers, like the last 4 years since we had this event. There have always been sessions on this stuff. The first generation is, most of you will know, RA Guard on a port level. Say drop inbound ICMP type 134, so router advertisements, just to guarantee stability of your network and to counteract rogue router advertisements. That has been the first generation, and then there has been, oh, by the way, this type of controls can, again, as Antonius will somewhat discuss later on, and it has been discussed at many, many occasions before, this can be easily circumvented by adding extension headers and or fragmentation to packets for the simple reason on the switch infrastructure level, you can't do reassembly there. You can't really do sophisticated operations with packets. Usually it's 1 gig ports or 10 gig ports, and you have to process in wire speed. So you really have, you just have ASICs looking at a certain offset within a packet, and oh, is there a 134 there? Then if the router advertisement, drop it. Once you can take this like decision, as maybe once the actual ICMP content has moved into a second fragment, these mechanisms fail. And there's no cure for that. The switch vendors won't come up with like an elevated or augmented RA Guard implementation, which can do reassembly. We won't see this for performance reasons. And the other cure would be, actually there is a cure on the recipient side. So hosts are supposed to immediately drop packets, say fragmented router advertisements. There is no need from a, say, standards and production level perspective to ever see a fragmented router advertisement. That's always an attack. So why not just drop it? This is specified in the RFC 6980. Unfortunately, deployment of RFC 6980, even though it's more than 2 years old now, is very sparse. Linux supports this, all others, to the best of my knowledge, and some testing we did don't, at least, I mean, I last checked in January. Windows doesn't, even BSD, we tested like a year ago, so it didn't at the time. This might have changed, but so keep in mind, this first generation, first hop security can be circumvented by an attacker. This doesn't mean you shouldn't deploy it, as it's good for network stability. It prevents like devices showing up and emitting router advertisements due to misconfiguration. But once there is a skilled and motivated attacker, this doesn't really protect you. And then there is a third and a second generation, which in Cisco space rely on a so-called IPv6 snooping framework, where you can do, like, you can counter NDP spoofing, not just router advertisements in DHCP, but NDP spoofing as well, and you can limit all types of interaction happening on the network. The problem with this one is maturity-wise and configuration. Maturity-wise depends. There's platforms which behave erroneously once you configure the stuff. It doesn't really do what it is expected to do. And the more important thing is it's complex configuration-wise. You don't apply it on the port level, but you have to come up with a so-called policy configuration, which then is applied to ports. There is a certain interaction between the port level configuration and the policy configuration, and once you have specific requirements, like be able to unplug a laptop from your desk and walk over where it is behind a phone, a hard phone, walk over to a meeting room where there is like cables and you plug into directly into switches. In Cisco space, this would, from mostly default configuration, this would fail. like the switching infrastructure would like, wait a second, this MAC address has been over there at that port before, and there was no link down up event as you were behind the phone, and now he's showing up there. This must be an attack. To counter this, you need even more configuration, which then again adds complexity, which then again means you can easily deploy it by means of templates, which means you can't really use it in an environment where you want to go with templates for several hundreds or even several thousands of devices. In short, we don't see this actually deployed out there very often due to these things. And actually, we recommend against using second and third generation first hop security for a number of reasons. Teething problems, functionality problems, and configuration complexity. We usually recommend, and this is what we actually see, just going with a switch port level approach of drop route advertisements, drop unauthorized DHCP packets, log violations by this global configuration command, and that's it. Don't use more than this. An additional note in this context, it might make actually sense to use RA-Guard in presumed v4 only networks too, as this means even if there is like dual stack systems or misconfigured systems or systems you are not even aware that they have dual stack after like a kernel recompilation or firmware upgrade, whatever, to just drop this type of packets, it makes sense, and we see this actually, that people enable RA-Guard on their switching infrastructure, even in segments where they think they only have v4, to be able to, well, if v6 comes in without v knowing, still network stability is, I wouldn't say guaranteed, but you help network stability by dropping rogue route advertisements. Another approach that we have seen discussed is drop v6 packets based on their ether type at the switch port level. The thing here is that we have a number of customers who want, especially to protect their what they call the production, so ICS, SCADA type environments. Where they have, this is, we only run v4 there, but we don't really know if whatever type of vendor, Honeywell or whatever, they come up with, these are devices we can't really control. We don't have full visibility what their stack does. If they come up with v6, drop it until we have deployed it in an organized manner in this type of networks. Unfortunately, this, from a technical perspective, good approach, dropping v6 based on the ether type, you can't really do this on a number of industrial switches, where it would be maybe most needed. So, well, to conclude this, at least for Cisco space, first hop security is a good thing. It should be part of your overall strategy. It's just the availability depends on the platform. I don't have new information than this one, which is from Cisco Live 2015. Eric, if you have any newer table, I've not been able to find one. I have, last year we had a discussion with Cisco on this type of stuff, and I got an email from a person very much involved in this. On the product management side, this email is from like I think it's October, maybe it's early November, where he was like, wait, FHS on Nexus still roadmaps. Look at this. This is 1 year old, and there it was like, well, we will have it in NXOS 7.2. 9 months later, the guy writes me, well, we don't really have it yet. It will be in 7.3. At least on physical Nexus platforms. Well, the other Nexus, which essentially means, most importantly for many people means, what about Nexus 1003? Maybe later in 2016. So FHS might depend.
What's the state of Nexus 9K?
To be honest, I don't know in detail. My understanding of when we had this discussion, this was mostly about 7Ks. My impression was 7K is a prioritized platform. It will be there first, and all the others will follow at some point. So I would assume 9K will be part of the other Nexus platforms sometime in 2016. But I don't really, I don't know in detail. When it comes to V6 or first-hop security in non-Cisco space, let me add that it's available, as I mentioned, in other Windows platforms too. HP has, I have to say, a very decent and mature, on those platforms that we tested at least, 5800s and some like 56 something. And what we've seen in customer environments, good first-hop security implementation. One thing to keep in mind here is, though, that they have a different configuration paradigm. On HP platforms, it's usually you enable the feature globally, a protection feature, and then for specific ports, you configure exemptions. You say, okay, drop all route advertisements except for on these ports. Whereas on Cisco, at least in the first generation, it's drop it on these ports. Which means you say, depending on how much you want to automate, or you go with templates, and there's always like a configuration mindset of operations personnel involved. The configuration paradigms of, at the time, HP, they have a RA guard command in the interim with like Conware 5.8 something, as far as I know, but no, I have to ask Chris on this. He will give a talk on this later on. Anyhow, they on very new platforms, they have a port-based RA guard, which they didn't have earlier. And this different configuration paradigm, once you have say a large environment with both HP and Cisco switches, which is not that uncommon. Well, the mindset of configuration of deploying first-hop security is different, which large-scale operations-wise might play a role. To conclude the first-hop security thing, I already mentioned MLD. From a security perspective, MLD is ugly. There is no, unfortunately, you can't really address it on a switch port level. You could do so by switch port-based ACLs, port ACLs, or VLAN ACLs, which from an operations perspective is probably not what you want to do. Eric and Antonius and myself, we came up with an internet draft. We strive at some point maybe to see something like MLD guard, which doesn't yet exist. And to be honest, this draft doesn't have too much traction right now. I will in ITF Buenos Aires in 2 weeks. I will present this in the OPSEC working group. We hope it will gain traction then, as we think it's important. But right now, you don't really have a cure against MLD-related stuff. At least what is a bit, I wouldn't say reassuring, but there's not many, except for Antonio's tool Kron. Most IPv6 attack tools don't have don't have MLD capability, so we don't see much attacks yet. But from the lab testing that we have done, and MLD is a nightmare security-wise. But it's not yet really there, so we might have time to come up with MLD guard still. So far, as for the network level, to very quickly let me summarize. There's three things which should be part of your IPv6 protection strategy. That is what can be done routing-wise. This propagate just some networks, or at least null route specific networks when packet enter your network. What can be done on a traffic filtering level on transit and first hop security. All these are network layer controls, and not least given I'm a networking guy, I think this is where IPv6 security starts. IPv6 security is not, okay, this sometimes happens depending on a wind, and we have this every year, and I always forgot how to, there is something which can be done. It has stopped now, hasn't it? Okay, at least. Let me think. At some point, I will be. Oh, this one, but the other ones. Can you still see this? And everybody? Okay. We'll take care of this later then. This was network level. And I think V6 security should mostly be done on a network level, not so much on the host level. Still, part of your say strategy and your discussion, and maybe there might be even a document like an IPv6 security concept. Still is wait a second. In the end of the day, we run systems providing services. Is there anything else which should be done on the system level, and what are the actual, say, imagine the networking guys have done their homework and implemented what is reasonable and what makes sense from an operations and benefits perspective. Is there any like dangers or risks left from a system perspective, from the perspective of guys actually running the servers? And say some discussion on this should be part of your overall strategy. Usually, when we do this, there's the reasonable assumptions for enterprise environments are IPv6 shows up in dual stack mode. We don't see enterprises, and we don't think it makes sense to go with V6 only. V6 only makes sense for like client-based networks and for some environments like telcos. And I mean, you might have noticed the Wi-Fi here is V6 only. The main SSID with a translator. You might even not have noticed, but like for a complex enterprise environment with a number of services and dependencies and so on, dual stack is pretty much the only way to go. Even though, from a long-term operations perspective, it might not be desirable, but it's a reality, kind of. Assume further first-hop security. There is some first-hop security. Assume routing layer security might be there, but the larger an organization, the more complex an organization gets, the less we see this usually, as people are really we don't know which parts of our huge network are going to talk to the outside world. So we can't really operate on this routing propagation level. And another assumption is, say, certain types of controls, namely intrusion detection and prevention systems, they have lower detection and prevention rates when it comes to V6. As has been discussed extensively at the V6 summit before, and there will be a session tomorrow run by Antonius and Raphael, where we have a tipping point there in a source fire, and you will see in real life. I mean, we didn't upgrade to the latest code. We might do some experiments, but we have been able, when doing lab testing a year ago, to circumvent pretty much all of them by means of extension headers. So it's a fair assumption. Whatever you have in place, it can't deliver the same level of protection as it has been delivering maybe in before, or not even there. But taking these assumptions into account, usually one can come up, if we have done this stuff as laid out in the former part of my talk, what else is left there from a host perspective? It's fair to say, I will discuss this in more detail in another talk tomorrow, where I discuss the host level perspective, that from a host level perspective, there's two main increased risks. That is interaction on the local link by means of malformed packets or by means of MLD flooding. And you might have a higher exposure when it comes to unauthorized access, as going with global addresses now, as opposed to RFC 1918 space in v4, combined with that some network level controls like IDPS systems can't do the same job as they have done before. It's probably reasonable to expect you will have more bad traffic showing up at those systems that have been there before in an IPv4 world. Again, we will cover how to tackle this tomorrow. So this leaves the question, okay, now we have mostly focused on what are the differences induced by IPv6, technical differences, which then bring modified level of risk. That said, and that discussed, can we just go on with our security architecture with the same firewalls, the same whatever types of technologies, content filter, URL filters, all these shiny blue, red, violet, purple, whatever types of appliances that we had before. I will very quickly discuss some things you should keep in mind. Let's phrase it like this. Unfortunately, we think you should rethink your security architectures now that IPv6 becomes a reality, as there will be some elements that might be part of your current enterprise security architecture that will be a very hard time working properly once v6 is there, for reasons I'm going to lay out in a second. And there might even be elements which can't deliver anymore what they have delivered as, say, protection-wise in the earlier days. So some paradigm shift might be needed. Let me lay out this very quickly in more detail. Right now, in v4 networks, you probably have, or most of you will have, security controls that rely on reputation, like reputation-based email filtering or reputation-based URL filtering. And probably you will have devices working in a stateful manner. Stateful firewalls, stateful inspection, and all this. When it comes to reputation, it will be very interesting to see how well a reputation-based approach will work in the v6 world. Many people doubt this. There is actually a working group at the M3, so the messaging, malware, mobile, anti-abuse working group. Those guys, industry consortium taking care of email filtering in particular. And they published a paper like, okay, what the policy issues for receiving email in a world with IPv6 hosts as, say, reputation-based filtering based on an address might become much more difficult with v6. Systems can have many addresses. Systems will have, like on mobile networks, every phone will have an own /64. So how would you filter on that one? Should we then say there is one smartphone, an infected smartphone sending unwanted traffic? Would you blacklist a specific address, which can change in a second? Would you block the full /64, which then means if you do the once the smartphone uses a Wi-Fi network where it shares a /64 with a number of other entities, you might have collateral damage. So reputation based on a, say, address level, both when it comes to email and when it maybe even comes to say web content, and especially like with peer-to-peer protocols, it will be very interesting to see what happens there. A number of people, including me, are very skeptic if this is going to work in the IPv6 world any longer. The other thing is, once you have stateful devices, the amount of state that a stateful device has to keep usually depends on the complexity of a protocol. Complexity of the protocol and the potential space of numbers involved. Both are much higher in IPv6 than they have been in before, which means stateful packet filtering might become much more difficult. We will see what happens again in v6. There is a well-known problem of neighbor cache exhaustion, which is simple state exhaustion attack. A device keeping information, a certain amount of information based on network behavior. In IPv4, with v4 address space, like there was an ARP state incomplete, but there was never high numbers of this. In v6, with segments being /64s by default, the potential number of incomplete neighbor cache entries gets so much bigger that just by this increase in number, certain denial of service scenarios can happen. Neighbor cache exhaustion is what I think mostly solves problem. But imagine what happens. There is an infected smartphone. This infected smartphone establishes TCP connections with one of your web servers. And for every of those connections, it fulfills the TCP handshake. And then it takes another address from the /64 the smartphone has at its disposal. So from 2 by the power of 64 addresses, it can establish a TCP handshake with your web server sitting behind your stateful firewall. Do you think your stateful firewall is going to cope with this very long? Probably not. And imagine, say, several smartphones do the same. And you won't even cure this by, say, once the mobile operators do source address filtering, as these are legitimate source addresses. It's just exhaustion of state on your stateful devices by seemingly legit communication. So whatever you do, please think about the security controls you have in your networks which store state. And then think about, wait a second, with v6, what is the amount of state we still have to store and which bad thing can happen? There's a very interesting case study from guys at the, I need another 5 minutes, so I should be on time. And we might even be able to do some Q&A. This is a very interesting case study where switches kept crashing in a lab at the MIT, and it turned out these switches were say keeping state of multicast groups, which in v4 is not a problem as there is not many multicast groups. In v6, there is a number of multicast groups, as every address present on a local link has the solicited node multicast, associated multicast group. And in this specific network, they didn't even have many clients, several hundreds. But those clients had iOS devices, iPads, smartphones, which when they woke up from being like, I have no idea how the state is called exactly on iOS devices. When they woke up on the Wi-Fi, they got a new address, including a new, or they got a new temporary address, which then meant there was a new solicited node multicast group, which in turn meant that the switches keeping track of the multicast groups had several thousand multicast groups within an hour to keep track of, keeping state, and they crashed. Actually, they did not exactly crash, but they used all the memory they had for this multicast groups, in a shared memory space with spanning tree. So multicast groups meant no space left for spanning tree process failing, and most of you will easily imagine what happened then. This is a classic, you can blame it on a window or whatever, this is a classic state problem. Collecting information on a device to understand what's going on in the network, and in V6 there is so much more of this information due to an unforeseen interaction. Nobody, like 20 years ago when V6 was invented, they didn't think about this, wait a second, solicited node means a multicast group. There wasn't temporary addresses at the time, and there weren't iOS devices. Some people could even blame Apple on this. Why do you generate a high number of temporary addresses per hour? Yeah, well, our users ask for saving battery time. So we sleep, and when the stack comes up, and all this, many players involved, in the end of the day, crashing infrastructure due to storing state. Keep this in mind, please do. I see a number of, lots of problems which we will face in like 3, 5, 10 years from this architectural space. Simplicity is your friend. You won't see a talk of mine without mentioning RFC 3439. Read it. First one, yeah. Guideline. Oh, that is. Yeah. It's sorry for being confused. I actually thought this was the wrong one.
No, it's 3439.
Yeah.
Top left, second.
Yeah. Okay. The one that I'm referring to. Okay. Now I realize I can't. I was looking for is. Wait a second. Is there any Bush? He's there, but from my angle, I can't see this. The main thing here is the simplicity principle. If you want to run a large-scale network, and with V6, just number-wise, you have a large-scale network. Even if you have a seemingly small number of hosts, the number of state entries and addresses which could be used and which might be used with not being under your control from like iOS devices or virtual systems using an address for each of the services they propagate, all this container stuff showing up at some point. You will have large-scale networks, and there is good principles for running those, and one of those principles is simplicity. Keep things simple. Don't store state. Keep this in mind, please. Once you have, you do stuff on traffic, like filtering, understanding what certain traffic is, or trying to understand, and then drop it or not, especially when it is based on signatures, like IDPS systems do. Look at the packet content, try to identify, oh, there's a bad thing in there, drop it. All security mechanisms which work this way will have very hard times in the near future for 2 reasons. One is more and more traffic is encrypted, so you can't really spot what's going on in there, which is not a V6 specific problem, or V6 specific thing. I don't think it's a problem. It's just, it means different security architectures required. The thing, what is V6 specific? Extension headers. There is so much fuzziness in how a packet could look like. It makes life for somebody, well, I try to identify this as bad and then drop it much harder. Which means, in the end of the day, you might move security functions, traditional security functions like filtering on content, on signatures, what is in a packet, you might move this to like to the endpoints. Not do this any longer on the network level. You will still maybe keep your so-called stateful firewalls, as PCI requires this, but don't expect certain types of devices to do much good in V6 networks. If you have an IDPS, either scrub extension header stuff before it enters the IDPS, or there is no, you can't really scrub traffic from extension headers, but you can drop it before it enters your network. Which brings me to the conclusions. I have one left before the conclusions. Given I mentioned do not use much state, go with stateless filtering. Stateless ACLs might be your friend once the stateful firewalls can't do any longer what is needed. And for many environments, stateless ACLs is good enough. Works, does what you would expect it to work.
How would you combine that with UDP? Because for UDP, there is no stateless.
Yeah, but okay, how much? Yeah, I mean, how much UDP do you have? That's DNS, SNMP. That's pretty much.
And SIP, RTP. All
well, okay, yeah. Then I mean, go with just. I mean, with a stateless, you can cover UDP. It's just you don't have an established keyword on the ACL level, which would be establish a state again. I mean, stateless is for UDP. That's a perfect fit, kind of.
right,
yeah. You have well, you lose visibility of traffic direction, kind of. So that is the pill you have to swallow. I think we will see, in general, a shift from UDP traffic anyway, given all these amplification problems. I'm a big fan of run DNS over TCP in the near future, but this is another debate. To conclude on the V6 thing, keep in mind, when it comes to these security controls, V6 is very different from V4. This might mean, in very short, don't just take your security architectures you have one-to-one to in your V4 world to V6 world. Think about suitability in the sense of what do we actually need and what can be reasonable be done in a reasonable way when it comes to operations and state. I will keep this for a second like this. This is my last slide. Yeah, getting back to the overall topic of an IPv6 enterprise strategy, there is 3 main pillars this one should be built on. That is, understand the differences and get an understanding what is relevant in a V6 network and which things might not be prioritized. Identify what is relevant, and therefore you need an understanding of the differences between V4 and V6. Second part, it's about network layer controls. That is where there is some this German saying, wo die Musik spielt. There is an idiomatic expression for this in, that is where where the rubber meets the, something like that. A network layer is where IPv6 security happens. Routing propagation, filtering, first hop security. And I would like to emphasize at this point, while many organizations mainly discuss first hop security, I think one of the most important elements, and this is a thing you should do today, before you have, in some of your environments, today is before you have widespread deployment of V6, come up with a proper routing strategy. You can save a lot of headaches and pain in the future if you do the right thing now, in both directions. If you act too strict right now, this might mean in 2, 3, 5 years you have to revert anything which is bad. If you act too liberal right now, it might mean you have to cure problems, unforeseen problems in a few years. This is a thing you should spend intellectual energy on. Thank you for listening.